Okay, so we will take a look at TensorFlow Playground now. Okay. Can you all see my screen? Give me a change that raised hand to a thumbs up if you can. Okay, cool. So this is TensorFlow Playground, right? It says tinker with the neural network right here in your browser. Don't worry, you can't break it, we promise. You should never make that promise, but there's a lot of things going on here, right? So what are some of the concepts that we covered here? Maybe we can just scroll through really quickly. We looked at, okay, perceptrons, multi-layer perceptrons. Within this, we saw we had an input, we had an output, we have some weights. We have an activation or a threshold function here. Some of the other things we looked at how the network itself trains forward pass and then backward pass, right? So that's how it learns. And on the backward pass, it updates its weights. But what are some of the other parameters? During the weight update, we have a learning rate, right? So that's one thing that we can tweak as humans. We have an optimizer. There are different optimizers you can choose. That's another thing we can tweak as humans. I think those are pretty much the main things here. So let's just, for today, for this quick, like 1 minute explanation, let's look at learning rate and activation. So I'm just going to completely arbitrarily pick some things here. So this is our data set here on the right. We have a bunch of orange points on the outside and blue points, right? So what is our goal here? Our goal is to create a decision boundary that separates the orange points from the blue points. So let's see what happens if we just run this for maybe 100 epochs with this kind of learning rate and this kind of activation. So let's take a look at what our network is before we get into the details. We have two inputs, x1 and x2. So x1 is the x-axis here, and x2 is the y-axis, as we can see here. So this is x1, where my mouse is, and this is x2, where my mouse is. So this is a one hidden layer neural network. We have 4 neurons in the middle, and we have 2 output neurons. Can somebody tell me, there's no tricks to this question, what are the 2 outputs here in this neural network? What do we think? Yeah, yes, the classes, right? Maybe be a little bit more specific, Yash. I think you got it. Blue versus orange. Yeah, exactly, right? So let's see what happens when we run this. Okay, so we're about, let's just let it keep running. We're like 200 epochs in, right? 199 exactly, I stopped it. So what do we observe here? We see that there's not really a good split. There's no real decision boundary here. It's kind of just like split on something that looks like almost like y equals x or something. We see blue on the left and orange on the right. There's no real good split that's going on. Somebody tell me what's something we could change here. What jumps out at you? There's like 3 main things that we can play with right now. Just forget about everything else. We have learning rate, we have activation, and then we have our network itself. So somebody want to speak up or throw it in the chat? Okay. Okay, some people say activation, some people say learning rate. Somebody want to expand on that? Let's start with activation, or actually no. Let's start with learning rate. Let's start with learning rate. So what can we change about the learning rate? Here are the options. So it's on the lowest possible option right now, 0.00, 4 zeros before the 1. Okay, increase it, Yash. What should we increase it to? 0.001. Okay, so I'm going down 2. Let's try that to start. Okay. What do we see now? We see like this y equals x kind of thing is forming a little faster. So we're converging on some sort of a decision boundary faster, but it's still not that great, right? We know that what would our real decision boundary look like? I'm just going to annotate here. We would want it to be something like this, right? So everything here we would want to be orange, and everything inside we would want to be blue. But we're not really getting that, are we? Our decision boundary is kind of just looking like a line. So let me see how to clear this. Yes. So what could we do? Yes, we want a circular, or Sanjana said something interesting. We want a non-linear decision boundary. So we changed learning rate. Okay, cool. Okay, and Shinmei nailed it. We won't get a non-linear boundary with linear functions. And by functions, I'm assuming he's referring to activation functions, right? So this is kind of what we were talking about in our part 1. Our activation function really matters because it's not only, I talked about how it was like a squashing function. Let me see if I can find that. It's kind of like a squashing function, right? Like if you have an output that's between -1000 and +1000, and you want a probability. Probabilities we know are between 0 and 1. So we would want it, okay, I can't find it, but we would want it to be squashed between 0 and 1 if it was a probability, right? So similarly here, we want a decision boundary. That was a side effect. We also want our activation function to help our network learn a non-linear decision boundary. So if we're always activating with just y equals x, the identity function, and we know that's a straight line, then we're not going to learn something non-linear like a circle. So let's see if we can change this activation function. We have 3 other options. What should we choose? What do we think? So we know it shouldn't be linear. A lot of you got that point. What could we change it to though? Anybody have any thoughts? Sigmoid. Okay, let's try sigmoid. First step, sigmoid. Okay, let's see what happens now. Okay, looks like we didn't get much luck. Also note here, we can see our test loss and training loss. So this will be very quick tangent. This will be useful for you in your part 2s because you'll be having these graphs like we were talking about in chat of test loss and training loss. So right here, we can see our test loss on top and our training loss on the bottom. So our training loss is like 0.49 and our test loss is 0.5, which is reasonable, right? Or we're probably going to do better on our training data than our test data. Our test data is the data we haven't seen. Our training data is the data that we've seen, right? But if our training loss is higher than our test loss, we'll talk about this in lectures to come. That means that we have overfit. This is a keyword here. It's called overfitting. This means we've overfit to our training data set. In this case, we see our training loss is less than our test loss. So things are good. But maybe if we run this for a few more epochs, we'll start to notice something interesting. Okay, looks like it just kind of stopped here. But if, this is a side note, if our training loss managed to surpass our test loss, if this line crossed over this darker line on top, that would mean that we started overfitting to our training data. So the example I like to give is assume, think of this like a practice test, right? Assume we had a final in Intro to Deep Learning. We don't. I'm not trying to scare you, but assume we had a final. Then if we give you a final practice test and you memorized all the answers, you would know all the answers to the practice test. You would be able to regurgitate the answers, but you didn't actually learn the concepts. So now if I give you the actual ideal final, which doesn't exist, and I score you on that, you might not do so well, right? Because if you just regurgitate the answers to the practice test, then you're not really learning the concept. So that's the idea of overfitting. If our model memorizes the training data and kind of just regurgitates those answers back on the test data, then the training loss will be higher, or sorry, the training loss will be, the training loss would be much lower than the test loss. I think I may have mixed this up. Yes, isn't there overfitting when training loss is less than test loss? Yes, that's correct. So the concept I was saying was right, but my words were wrong in that one part. So just to make sure I didn't confuse anybody, if your training loss is far less than your test loss, typically it'll be a little less, but by the strict technical definition, if your training loss is less than your test loss, that means you're overfitting. And how much you're overfitting by is defined by the difference between your test loss and training loss. So does that make sense? If you're overfitting, that means your training loss is less than your test loss, not more. Okay. Yeah, thanks for catching that. That's important. Okay, cool. That was like a huge side tangent. So what do we have? We changed our learning rate. We kicked it up a notch, 2 notches actually. We went from linear to sigmoid. Now let's try 10H, right? This is one of the 2 remaining activation functions we have left. So let's try running this one. Okay, we're around 100 epochs. We see something coming into view. We're around 200 epochs, 300 epochs. So we're getting somewhere. Let's try kicking up the learning rate a little more. So we'll go up a little bit more. Now when we run this, boom, right? Around 200 epochs, we start to get some sort of an interesting decision boundary. And what do we see that's going on with our test loss and our training loss? We are actually overfitting to the training set because like we just talked about, our training loss is less than our test loss, but that's fine. At least we're getting some sort of a pattern here. Now let's see if we change 10H to ReLU, what happens. We can see we start to form a perfect circle, and it was really efficient in less than 100 epochs, maybe even around 80 epochs. We formed this almost like pentagonal or hexagonal decision boundary around the blue points. So boom, this is what we needed. And if you play around with this, you'll see that there are ways to do this even faster. So maybe one challenge to you guys is try and see if you can get this this kind of circular-ish decision boundary in less than 50 epochs. Then try to do it in less than 30 epochs, right? There's a lot of clever things you can do with regularization. Regularization, we haven't talked about this yet. We will in future lectures, but it's basically a way to make sure you're not overfitting to your training data. And you can try varying your features, right? So if you apply some sort of a transformation to your input, sine of x1 or sine of x2, or maybe we increase the number of hidden layers, right? Let's just see what happens when we do that. Okay, we get it in around the same number of epochs, 90-ish epochs, but we can see that there are some changes going on when we change the structure of the network or any of the hyperparameters. So that's basically a not so 2-minute, maybe like 10-minute explanation of TensorFlow Playground. There are a bunch of different data sets you can use. I encourage you to try the spiral data set. That one is the hardest one to do. Yeah, so that's TensorFlow Playground. Any questions?
Hey, thanks, Roshan. Yeah, just to summarize, so the main point of TensorFlow Playground is just to like plan your models and design them before actually coding, right?
Yes. So it's more educational. It's not really meant to help you in your yeah, thanks, Dan. I should probably summarize. So this is more of an instructional thing. It's meant for you to get an idea of what you'll need to be doing when you actually start your homework P2s, because all of this stuff is kind of nice and fun to play around with in the web. You can't break the network, but when it comes to the P2s, you can definitely break your network and do all sorts of interesting things. So this is meant to kind of introduce you to the intuition that we want you guys as students to develop from the homework part 2s. And in homework 1, part 2, you'll be building your own multi-layer perceptrons and playing around with different activation functions and all of the parameters that we played around with and possibly more. That's what you'll be doing on all of the P2s starting from homework 1, P2. So just a quick intro demo to that to show you that all the stuff we learned today aren't just, mathy concepts, that they actually help the model. They help you create machine learning and deep learning models to learn on real data sets. So you'll be doing this in the P2s. That was the main point of this. Does that make sense?
Yeah, it does. So in P2, like when we're following the instructions and everything, will it be kind of self-explanatory at which point this would be beneficial to like use and to dive into?
What do you mean by this would be beneficial? Sorry, I think I lost you there.
Like, I guess I'm trying to understand if it's not used for like planning out an actual model that we're going to code. You say that it's useful for building the intuition, but I guess what isn't intuitive to me is when we like know to go and start to play around with this. Is it like when we encounter a description of a model in an assignment and then we want to go and like investigate further, and so we go to TensorFlow Playground?
Right. Okay. So just to clarify a little bit more, this is purely instructional because all of the data sets that they have are pretty made up, and this will only get you so far in terms of intuition, right? This is more of like a set of examples to show you what a neural network would look like without you having to actually train it. So for homework 1, part 2, when we give you the data set, it's going to be completely different. You're going to have to build your own model from scratch. This is just meant to show you, to give you a little sneak peek of intuition into, for example, one key concept you might take away is, okay, as I increase the learning rate, my model trains faster. We didn't go to the other end of the spectrum, but I could have also showed you if you increase your learning rate too much, your model might miss the solution altogether and just bounce around, right? So one takeaway might be you need a Goldilocks zone learning rate. Another intuition might be, a linear activation cannot help you to learn nonlinear decision boundaries. So it didn't work on the circular. It definitely won't work on the spiral. So these are like very broad takeaways that you can get from any sort of ML thing, ML playground type of thing, like TensorFlow Playground. But to clarify, this is not something that will help you with your P2s. It's just purely an intro to neural networks. Does that make sense, Dan?
Yeah, it does. All right.
Okay.
Thanks, Roshan.
Sure. All right.
What is the difference between linear activation and ReLU?
Right. So ReLU stands for rectified linear unit. Let's take a quick look at what that looks like. So it looks like this, right? So this helps us combat something called the vanishing gradient, which we'll look at later, probably way later. But basically what this means is if your input is greater than or equal to 0, it's just y equals x. So if your input is anything above 0, like let's say your input is 2, then this activation function will just give you back 2. It's purely linear. But if it's anything less than, if it's a negative number, or yeah, a non-positive number, it's going to be 0, right? So anything 0 or less will just go to 0. So it kind of like reduces away negative inputs. I wouldn't worry too much about this one just yet. We may talk about this a little bit more in the homework 1 part 2 bootcamp, some of the intuition behind different activation functions. Does that help, Madhav?
Yeah, and linear is basically just like this line going ahead, kind of.
Yes. So linear just means like identity activation. There's no activation function, in fact.
Okay.
Y equals X. Yeah.
Just to follow up to what Dad asked earlier.
Mhm.
So, I mean, we did talk about that. If we have a nonlinear decision boundary, we do need to have nonlinear activations. But if how do we relate that to nonlinear feature? So, for example, I believe if we have, for example, the current one that you have, the spiral up there,